Okay, cool. So you're welcome to, of course, ask any questions during when I pause, or raise your hand if you would like to interrupt me as well, and put your question in the chat, and Nathan can read it out to me. And of course, we'll have office hours to discuss even more in details. So we saw in the last lecture in details how do we generate the quad IR from ASTs. What we do typically there is we descend down the AST. We visit each node, and depending on the type of node it is, we trigger different code generation procedures. There are code generation procedures for sub-expressions. There's code generation procedures for assignment statement, L value, R value references of arrays, how to compile them down. And we also saw different control structures, such as if then else. We saw for the while loops and so on. And of course, I had left some things to you to be able to compile to understand it on your own by reading those things. By the way, by now, should have pretty much completed the reading of what I had given as a recommendation. Mainly do it just cursorily if you have not done it, and mainly focus on the semantic analysis IR side, because that's where this course is really beginning. So finish that off. And some of it we'll ask you in the homework to how to write the code generators for certain types of constructs. In each of these, we saw that we generate temporaries to hold the result of the current sub-expression, etc. And then we send that back as a result of the temporary name to the caller of this particular generate function. That's where that gets used. And from there, we generate further code. We also saw how to implement short circuits, Boolean operators, and so on. So it is pretty interesting, and it pretty much covers all the stuff that we do. And as you must have realized here, we just do all of this within a function call, and we are generating these quads within a function or a procedure call. Whenever we encounter the call itself to be processed, what we do is we take each one of these parameters that could be expression, so on. The function name itself might have to be evaluated. So we generate code for doing that, as you saw in the processing of the function call. And then we have pseudo instructions for call and return, which send the values, etc. So that's roughly what covers the function calls as far as from the caller and callee side. And each one of them has its own code. It's demarcated by the function name and end. So within the body of that is the quads which implement that particular function. And mechanisms for call themselves are implemented using first evaluating the function name, which could itself be an expression, and then the parameters, and then pushing them through a abstract instruction called push, and then making the call, and then waiting for the return value, and then assigning it to the left-hand side variable if it needs to be assigned. That pretty much, and then there are several constructs there which we haven't focused on or looked at, like case statements or switch statements, but they are fairly easy to understand. Some of those I'm expecting you to understand through this homework and also doing some reading on your own. And with that now, we will move on and we'll take the next step of what we call as converting this IR that we have into a hierarchical form for doing the analysis. And that's what this topic is. It's going to go on for a while, and we'll stay with the slides here, and we'll also read some of it through the book and also through a paper by Tarjan on the generations of the dominators, a classical paper. So what we are looking at here is what we call as, in general, a flow analysis, which is broken down into two parts. One is about the control flow. That is, how do we move from one point in the representation of the IR to the next point, and that is given by the control flow analysis. And that is as far as the transfer of control is concerned. But concurrently, along with that, of course, as you know, there's a data flow, which means that the values are fed from one IR statement to the next IR statement, and so on. And that leads to the data flow. Or if we are jumping from one place in the program to the other place because of if then else or some kind of conditional or unconditional branch, then along with that control flow from the last instruction where we were to the next instruction where we are jumping, we are also going to carry certain values which are prevalent there, and that's the accompanied data flow that occurs along with the control flow. So and in turn, of course, the control flow is also dictated by data flow, especially in the conditional branch sense, whether or not the predicate evaluates in one direction or the other. And this all leads to very fascinating characterization of the program in terms of which value is going where, and what can we do about that in order for us to gain an understanding of the program. And with this understanding, which we call as flow analysis, we do certain optimizations and or transformations. Really, optimizations can be broadly characterized more precisely as transformations of the program. So for example, we might be able to get rid of one operation in the IR. We might be able to do that to save certain cost. We might be able to move certain IR operation out of the loop. So therefore it executes only once as against so many times inside the loop. We might be able to replace one operation with the other, and that is called a strength reduction optimization or a transformation, and because of which the new instruction will execute much faster. The example of this strength reduction is a simple one which you already know. So if you have, for example, multiplication by 8 to any given operand, 8 the constant, you can convert that into a left shift operation by 3 bits. So that left shift operation is much faster than the multiplication, and you will be able to what is called a strength reduce the program to execute it faster. Now, of course, you may wonder, it is very specific to 8 or powers of 2. How do I achieve this type of a program which has these kind of constants? Well, preceding this, typically there is yet another optimization, which is to replace certain operands with their constant counterparts if we can find those. And that analysis is in terms of whether or not this can be replaced by a particular constant. And that is pertinent to the data flow in terms of what values are sending this at a particular point, the operand of that instruction. We do this transformation, I call this as transformation, in different scopes of, we can do it within a simple set of linear statements, or we can do it on a whole procedure basis, or even we can try and do this transformation by analyzing the whole properties in terms of the whole program. And therefore this analysis is called as either a local analysis or an interprocedural analysis, or intra-procedural analysis, depending on the scope of where we undertake this analysis. You might ask the question that, oh, why do we need analysis? Why can't we just do the transformations? And we'll seek answers to that question. Why do we need analysis? Why do we need to find out what happens when and how? And then be able to use this information. That is one of the most important reasons for converting this quad IR, which is in a simple form of linear form of top-down arrangements of IR statements, which are interspersed with some control flow into another form. So to summarize, we want to understand the control structure of the program, and we build a control flow graph. The control structure is typically limited within a function or a procedure in terms of how do we go from one point in the program to the other. We build that and represent that. And across the function calls, we typically have what is called as a caller-callee relationship. There is an edge from a program point which we have a call, and that takes us to the function which is called, or a procedure which is called, and that is called as a call structure of the program. So we have a call structure or a call graph of a program at a function to function or procedure to procedure level, and then each one of the functions or procedures is represented in details through its own flow graph, which is typically at a much finer granularity. It's not really exactly at a granularity of each IR statement, but a group of IR statements. We will pick that and we will try to go those IR statements into what is called as a basic block or a linear set of statements, and then we'll arrange the relationship between these basic blocks. So the control flow graph is, in short, inside typically inside a procedure call, and is a graph of basic blocks. Using this representation, what we built as a control flow graph, we will do the analysis of scalarized IR at this particular point. We know that we have taken the array references or structs or unions or any of these aggregate forms, and we have converted them, broken them down into the scalar form, which is a single value flowing through the program, and in terms of a temporary name. And that representation is, of course, used for, along with the control flow graph, to find out which value is going from where to where. And using this, if we understand that some values are going like this, they're originating here, they're traveling like this, they are going from this source to this destination side like this, and being transmitted further through their copies or whatever. We understand then that these values are what we call as reaching certain parts of the control flow graph, and using which values are reaching where, we will undertake some transformation. So that's the big picture of what is happening in terms of the data flow and control flow analysis. The control flow analysis sets the stage for data flow analysis, which follows from it. And our main goal is, of course, to really figure out which data is traveling from where to where, or which value is going from where to where. Any questions about this overall big picture in terms of what we are trying to accomplish? And of course, we'll look at why we are trying to build this. If we don't build it in this way, what will happen? And those issues, we'll get into that just in a minute. But are there any questions about this big picture that we are trying to undertake?
There are no questions in chat. If anyone
Okay.
wants to ask things with us.
All right, we can of course revisit this once we develop
So
some
I have a
details.
question, Professor.
Go ahead.
So I understand why we need control flow analysis and data flow analysis, and then I think you have mentioned this a little, but it is still ambiguous, the relationship between control flow analysis and data flow analysis. Is it like totally independent of them, or like how can I understand the relationship between those two?
Yeah, so they're independent of each other, and we'll see the details just in a minute. One is really about whether we can go from one point in a IR representation to another one through a transfer of control. And we'll build this first without paying any attention to the predicates, etc., which form the conditionals. We will not worry about which are the operands in the predicate, as you'll see. So we will have, for example, if such and such predicate is true, then go to this label, considering this type of statement. We will assume that the predicate, of course, can be true or false depending on the programmatic instance. And we will build here a representation that, assuming it is true, we will do a jump to a certain label. Assuming it is false, we'll have a fall through. And so there'll be two control flow edges coming out of this type of conditional statement. And we'll build this representation assuming such possibilities. And that's the way we'll first start. And then using this representation, we will see which value we'll be able to go from where to where. We'll be able to travel along those edges and carry the values. So that's pretty much how we'll do it. And in case we need to build any specialization that we need to incorporate certain properties, we'll do some more advanced analyses which will rule out certain predicates evaluating in one direction or the other in some specialized cases. We'll also try to account for certain other properties which we might have over approximated. I will talk more about that particular part, but just to answer your question at a high level, they are independent and the control flow analysis is the starting point.
All right, thank you, Professor.
Sure. All right, so let's move on and let's get first a feel of what exactly and why we are trying to do this analysis. I think that is really a very, very important question because it also sets the stage for how we do it and what kind of assumptions we had to make in this particular case. So, so we'll start with this simple example here, which is a very classical example which is used. And we'll try to seek some answers in terms of our, again, ultimate goal of all this is to be able to modify or transform so that we get a better program in terms of its efficiency and so on. So you can see here a group of statements, which are very simple at the IR level. We have, for example, assignment to A, assignment to B, and we call these as the definition of A or definition of B in our terminology. And that definition is associated with what we call as a program point. So we may have lots of different definitions of A in this particular representation at the IR level. But we are particularly caring about the definition of A at statement S1 here. In this case, it is evaluating to a constant. It need not be the case always, because you can see that in the statement SK, we have an assignment to C or a definition of C, which is coming out of A plus B. And in general, you can see that different instances of execution of SK will lead to different values of C here. In other words, depending on which values come in into A and B, uh, we will have different values of C, even though they are all originating at the statement sk. So what is the thing that we try to do in our case here? We try to look at what is called as a static property of the value rather than any dynamic property, because we don't know what will happen at runtime, whether the static property will evaluate in only one particular way or different ways. That will be decided by the kind of value that is participating at that particular point. In short, to distinguish between S1 and SK, you can say that even though the S1 may execute multiple times during the execution of the program, every time it executes, it will always assign a constant 2 to the variable A. Whereas in terms of SK, that won't be the case in general, because at one time during execution, we may have a value of A here, which is 5, let's say. Another time we may have a value which is 10, and these two times is the same statement sk executing for two dynamic instances will generate two values. Now, what is the purpose of this analysis? The purpose of this analysis is to figure out, can we statically assign a precise property as much as we can to determine a particular value? So some questions that we may want to answer here is this. Consider this simple program excerpt again. And it appears to us through a glance at it that since A is a constant, since B is a constant, maybe C is also a constant. So can we say that, first question is, can we always say that A is associated with 2 at the top and B is associated with 10? Always, that means independent of the dynamic instance. The answer to those two questions are yes, because they both are assigning a constant. Different constants, but both are constants nevertheless, and there will be different values. Now, if we ask the same question about C, will this be a constant, and what will be its value? And the answer to that question is, okay, what is going on here between S2 and SK? That will determine whether the C is really a constant or not. If you see in this particular case, if you have a linear set of statements, A followed by B followed by something and so on, and if A is not redefined between A is equal to 2 to C is equal to A plus B, then you can see that yes, that value of A will always be the one which will participate at SK, and that value will be equal to 2. In a similar way, the value of B which participates at that particular point will always be a constant which will be equal to 10. So we could safely substitute in such cases A by 2 and B by 10, and therefore we can even evaluate C to be equal to 12, and therefore C will be equal to a constant, provided these two conditions are true, that we are not assigning any other value to A between A is equal to 2 to SK and B is equal to 10 to SK. And this is only one of the conditions. What is the second condition? The second condition, which may not be that obvious, is A is not coming to SK by any other route except by this particular route from top. Imagine there is some branch which is bringing control in between S2 and SK. Then what will happen? When that branch takes place, along with that branch, maybe there is a value of A which comes along with it, which is not very difficult to construct an example. So that value will be brought along with that branch and will be fed to this A. And therefore, when that branch executes, or when the control flow at runtime comes along that particular branch, maybe there's a different value of A which comes along there and which is not equal to 2. So because of this reason, then we cannot substitute A by 2. And in a similar way, one can think about that branch might bring another value of B over there and will not be able to substitute B by 10. And therefore, we cannot proclaim these two as constants or even one of them. And if we cannot proclaim them as constants, then we will not be able to transform this C into a constant. So in short, the necessary conditions which are important for these transformations are that this should be a linear flow of control, A followed by B followed by something, and there could be other statements there which are not redefining A. We could, of course, use A, we could use B, that's all fine, but we should not change A, we should not change B. Those are one set of conditions, and those should be linear, so that when we start executing this code, we just keep going on and on and on, and finally the value of A which is fed here is the one which is coming out of S1, and the value of B which is fed here is only coming out of S2, and since those two are 10 and 2, we'll be able to substitute them and change this C into a constant and make it 12. Now you might ask me a question that, oh, so what is such a big deal about replacing this C by a constant? Well, you can see that in terms of code generation, it has implications because first of all, we are able to get rid of the addition operation here. We are able to figure out that C is a constant. Immediately, once we know C is a constant here, which is 12, we are also able to reason about this loop, which is coming down from there, which is small, which becomes a very small loop from 1 to C. And we may ignore it for doing any optimization because small loops may not have that much bearing. If, of course, the loop had millions of iterations, then we would worry about doing certain changes for optimizations. The optimization is a very tricky framework. As you can see, it entails all this analysis and then more in terms of actually carrying out the transformation and the optimization itself. And all that leads to a tremendous amount of compilation time. So in short, the optimization is not applied in many cases for very large programs across the board, but we figure out where the optimization may make a big difference. We figure out which loops are big, where the optimizations can play a huge role in execution time, and small loops like these we can ignore. So even to decide that, you can see here that constant propagation, which is the optimization which will here, needs to be carried out in order to find out which values are changed to constants, which values cannot be changed to constants. If they are both changed to constants, can we fold them and maybe propagate C further wherever it is used and fold it further and so on. And it leads to a lot of elimination of generated code. And secondly, since these constants participate as a part of IR, so let's say that in this particular example, for whatever reasons, A we were able to propagate as a constant, but B we were not able to propagate as a constant. We would still have a better code here when C is equal to 2 plus B. Why? You can easily see that those of you who have worked on the assembly side, whenever there's a constant participating in an IR instruction, we have very nice code generation possibilities, add immediate, subtract immediate, all these kind of instructions are possible, which take much lesser time. Multiply immediate especially can be much faster than trying to multiply two operands, and because of what we call as those instructions executing much faster, we have a better code. So constant folding, constant propagation, these type of optimizations lead to better instruction selection, better instruction generation, and many other advantages. You can see that when we move something as a constant, we are getting rid of one of the operands. So register pressure goes down because of that particular reason. Otherwise, we would have to hold A and B in registers for this type of architectures. And that will also lead to a lot of spills and other secondary effects. So register pressure goes down, instruction selection becomes better because of add immediate, load immediate, multiply immediate kind of instructions. And many times it helps to, of course, completely get rid of the operations, especially in the folding sense here. And then it also allows us to rule things like that this loop is small in this particular case, determine maybe even evaluate some predicates. For example, if we had a predicate downhill from here, A less than B, and that predicate we will know that we'll always evaluate to true. Because A is equal to 2 and B is equal to 10, we will be able to compile time evaluate the predicate. And in that case, we'll be able to simplify the control flow graph by using such results. So lots and lots of advantages. So this is a pretty foundational type of analysis which stems from what is called as a reaching definition analysis. But important thing to note here is this, that if we do not know the control structure, that is the point I'm trying to make. We do not know that S1 followed by S2 followed by all the way down to Sk are simply linear set of statements, and there is no control flow coming in between S2 and Sk. Then only we can carry out this particular substitution of this A by 2 and B by 10. Now, what if we find out there is actually a control flow that is coming in? So first of all, we must find that out, because if we ignore it and actually there is a control flow which does bring in a different value of A here, then we'll be wrong. So in short, for doing any transformation, there is a mandate on us to ensure that we must find out about the control flow. Because if we do not and ignore it, and somehow the control does come in between S2 and Sk and brings in totally different value of A, and if we ended up substituting A by 2, and if A were not equal to 2 in that particular case, we will be causing a semantic change in the program, and that will lead to a problem. So in order to keep the semantic soundness and correctness of the program, etc., we must find out about the control flow. There is no other alternative here. That is one really important point I want to emphasize. And then if we somehow find out that yes, there is a branch here, then what could we do? Well, we'll have to analyze what that branch brings in along with it. If that branch brings in a value of A, which is different, potentially different than A is equal to 2, then we cannot change this A, because that A will behave differently at A than the one which somehow comes in through S1, and we must account for what that A is. Now, if we find out that yes, that branch brings in an A, and if it is also found that it is equal to 2 for some reason, then again it is safe to change this A to 2, because in either case, the A, no matter which A we are talking about, whether it is from S1 coming down or from some other program point, both are bearing the same value all the time, and therefore we can change this A to a constant 2. So we'll be able to maintain constant propagation even under that particular condition, but only after ascertaining so. So that is the reason to find out the control flow, to find out if the statements are behaving in a linear manner. If they're behaving in a linear manner, we know that there's only one way the data flow will occur, from top to the bottom, because they will start executing. Let's say before S1, A assumes some other value. And the moment we then enter this S1, that value will be changed from whatever it was to a is equal to 2. And from there, it will flow as a is equal to 2 and go all the way down to sk plus 1 as a equal to 2. And so whatever value came in before this at S1, it just doesn't matter. So these linear group of statements also shield us from worrying about, hey, what may be going on outside it, because whatever value is coming in before this block of statements, it doesn't really persist. And the new values A1, A equal to 2, B equal to 10, they will be the ones which will persist within this group of statements and will lead to the A's and B's being assigned to 2 and 10. So that is the reason why we should try to find out the linear group of statements because of this shield. And then whenever it is not linear, we need to worry about what the branches are, what they bring in, and so on. Okay, so this analysis is basically the control flow analysis and is done to figure out where we'll come from, what will happen, etc. And then based on these, we will try to flow the data along those edges and so on, different paths, and we'll propagate that and we'll figure out which data is values are coming in where. And this is the reason why we will try to do it this way. So before we go further into exact representation, which will follow now, are there any questions about in general what I mentioned? Because this is the heart of it, is the motivation, and it should be very, very clear why we are trying to do it. And this also dictates later how we are trying to do it. No questions? Okay, good. So
Nothing on chat, so you're good.
All right, so let's move further. And one thing that we do this transformation, and then we'll get into the control flow analysis, is that, of course, important thing here is to preserve correctness. And that is what I mentioned just now in terms of making sure that we don't change this A when we shouldn't have changed it. So that's the important part. And so that is at the heart of this analysis. And second is, of course, doing this change improves the performance of the input program. Just because we have a property of something, if we do not use it to do the right kind of change, for example, if we do not reduce the operation counts or instructions complexity, etc., by using this transformation, then we'll be degrading performance, which is obviously not a good idea. And so these two are the constraints of preserving correctness and improving performance that guide the optimizations. And so that limits the space, because those are the constraints which we are going to worry about. And we try to improve the code here, and that is why we call this as optimization, as a relative performance improvement. For example, going back to our this thing, compared to the original code, which needed generation of instructions for adding A and B. Now, if you propagate AS2, we'd be doing add immediate here. That instruction will execute faster. So it is a better code in terms of the performance. There's no claim of optimality, that this is optimal code. Many times students write answers that, hey, this is optimal code that is generated for this program. There is no such concept here. This is not a theory type of setting here that there is a optimal algorithm which meets the complexity in terms of its load, etc. We don't have such things about the lower bound on the performance of a program. So to call it optimal, we can only say we have bettered it And so this leads to plethora of papers that, hey, my work does a better optimization than yours. How? Because I'm able to reduce the program's complexity more. Have I reached the end of the tunnel, and is that the absolute best? No, there is no such characterization, and there cannot be any. Because there are just so many moving parts and like registers and instruction selection and all kinds of different things which participate in terms of the performance side. So note that we are trying to get things better and better. And of course, the big thing here is we don't want to violate the program semantics. Okay, motivated it earlier. We are going to look at the concept of what is called as a basic block. And as we have seen it, the basic block is a sequence of consecutive IR statements in which the control flows linearly. That is, it enters at the beginning of this block and leaves it at the end. And there could be this particular statement that I have mentioned is simply a specification, as you can see here. And even single IR statement could be a basic block because it satisfies this, that it comes there in the beginning and leaves at the end and flows linearly. But what we are really looking for here is a maximal basic block in terms of trying to generate the intermediate representation. So this specification is now applied and we want to generate the maximal basic block. What is a maximal basic block? It is a set of such statements and you cannot extend it at the top. You cannot add one more statement before it and still preserve this particular property that the control flows linearly. And you cannot do it at the bottom as well. You cannot add one more statement at the end of it and preserve this property. So that is why it is maximal. And that gives us a very nice characterization in terms of optimization, because now we have a large number of these statements, as many as we could potentially have, to be able to apply this property of what we saw earlier. So for example, here, we could have simply said A is equal to 2 is a basic block. Fine, we just worry about that. Can we do anything useful with it? No. B is equal to 10 is a basic block. No. But now when we can claim here that the statements from S1 to SK, they're all a part of a large, big basic block, we can do something about it, and we can certainly carry out this constant propagation and folding and so on, this property across a group of statements which are forming this maximal basic block. So our goal here again is to find the maximal basic block, and the algorithm that we are going to look at is exactly trying to do that. And how do we then find this particular thing? This maximal basic block has to have something going on here which violates this property of linear flow of control, and that's the property which we use. And the property being violated of non-linearity of going from in the lexical order from one statement to the next in terms of its execution leads to this particular characterization, that only the last statement of a basic block can be a branch statement. Okay, and that terminates this linear property, because if it's a branch, then the statement following that is not going to be linearly executed. If it's a conditional branch, it may execute if the branch is false, but there's no guarantee there. We're looking for a guarantee here. And if it's an unconditional branch, then certainly the control will flow away somewhere else, and that statement will not execute. So that makes this last statement must be some kind of a branch statement which has a transfer of control. And in the reverse sense, since we cannot go before this particular basic block, Imagine what would be the disturbing problem there. The disturbing problem there would be that somehow the control came from somewhere and landed there, which means the two statements, S1 and S2, did not occur in a linear sequence. Suddenly the control came out of nowhere and hit S2, and therefore S1 and S2 cannot be in the same basic block. So a new basic block must start with the target of a branch. So these two, one defines what is the end of the basic block, one defines what is the beginning, and these are the markers which are used to produce the boundaries of the basic block, and everything in between is a linear statement that executes from top to the bottom, and that is characterized as the algorithm for generating the basic blocks. And this question gets asked many times, that what do we do with the function calls or procedure calls which also lead to transfer of control? The answer to that is simple. It depends on the type of analysis that we are trying to do. In most cases, the analysis that we are trying to do is not interprocedural, as I was trying to point in differences last time in the couple of slides back. So the analysis is typically intra-procedural, and so in many frameworks, we'll simply treat this particular statement as a huge kind of call, but we will not maintain some flow properties across that statement. So for example, things could get modified within the function call, and we'll not treat that as simply like any other statement in which things don't get modified. So by what I mean is, let's again go back to our example. So this statement, consider A is equal to 2 here. So what it is doing is, you can see that only change it is doing in terms of the value assignments is that it is taking current value of A, destroying it completely, and putting a new value in it. As far as other values are concerned, it is not doing any change to them. And so they will preserve across the execution of this statement. And that's typically how we treat each one of the IR statements in terms of how it modifies the values, especially the value which is on its L value side. But if this were a function call now, imagine that S1 itself or S2 is a function call foo. Now, as far as if we treat foo as a part of the basic block, whether foo preserves a value which is across the call, well, that really depends on what that value is. If it's a global value and it's allowed to be modified and is modified by foo, it does not preserve it. If it is not a global value, if it is not allowed to be preserved, it will preserve it. If the function call has no side effects, it will preserve it, and all kinds of questions therefore occur. And then sometimes foo might be even a library call that we may not have a source code. We can determine if something is modified by a call or not by looking at the body of the call and binding of the variables and etc. But if it's a library call, it's a binary which is available to us, which occurs many times. It is beyond compiler's control to find out whether the value is modified by that particular call. And therefore, the safe assumption that is made many times is that the value is modified. And that's how the call is treated. But that modification of a value, what that statement does is really a data flow fact. It's not a control flow fact. And we many times simply assume that these function calls are a part of the basic block. Now, there are examples of languages in which this execution characteristic of a call returning back to its call site is not entirely preserved. Set jump, long jump, and exception handling and all other irregular types of control flows will mean that this call will disappear somewhere else in terms of execution rather than returning to the call site. And in such cases, this call should not be treated as a part of the basic block. So the basic block will get terminated before the call. The call itself will be the new basic block. Fall through edge of this, if the call returns back, it will be a next edge which will join to the next basic block. Otherwise, the control will go along and there will be a termination edge at the termination edge of the program. So in such cases, the procedure call should not be treated as a part of the basic block. But those are complications and specific to certain languages which exhibit such type of a behavior. In general, for most of the function call, all other cases rather, will be treated as a part of the basic block, but its data flow will be treated differently. Now, to again recap, we are looking.
Just one question, Professor. Someone asked if function inlining can help represent procedure calls in a basic block, or how that changes things.
Yes, a good question. So function inlining, for those who may not know about it, we'll take the body of the function and we'll put it over there. We'll put all the call of this function at the call site. It will certainly enlarge the scope of our analysis because now you can see that we were treating this data flow fact in a different way. If you were a call in the absence of analysis, we'll have a more precise data flow fact because of the inlining now, all the blocks of the function being present there exactly, and we'll be able to analyze this much better by doing this inlining. So that is why one of the few phases of the compiler in the early phases after doing ASTs and all, they will do some pre-processing by doing some inlining, and they will generate bigger size of an IR. Of course, inlining means you take the body of the function and replicate it maybe at different call sites. So if we have 5 call sites, we'll have 5 times code growth because of replication. But we will also have these much nicer data flow facts because they are present at the point of analysis, and we will not have to make conservative assumptions. Of course, assuming that these are not library functions for which we don't know their IR. So that's what will happen there. So coming back to the point I was making, again, the goal here is to make that the basic block is maximal, and that is why this particular definition. And so we use this definition to therefore take this specification and of basic block, what it should be, apply this definition of a maximal basic block, and then come up with an algorithm which is pretty simple. So our goal is in this algorithm is to identify what is called as a leader of or a starter of a basic block using the rules, and you can see that there are very simple algorithmic rules which are very quickly applied. So we are again trying to do this analysis, as I mentioned, within a function call or a procedure call to build this representation. Across function calls, we have a call graph representation. So the first statement in a program or in a procedure call, or the analysis unit as we call it, is a leader, because that's where we will start execution of that function call or a procedure call. So that is the beginning of a new basic block there. The second way a basic block is brought into in effect, as we said, because of the definition of maximality here, that is the target of a branch is a leader, because you could see that the previous statement and this current statement could not be in the basic block, same basic block. The extensions upwards is stopped because of the target, and therefore that starts a new basic block here. Because you can say that S2 executes now, but without the execution of S1, if the target is on S2. And so therefore S2 will start a new basic block. So those are the two starting points of a basic block. This target of a branch will be a label for our IR most of the times, but not all the time, in terms of depending on where this algorithm is being applied. If it's being applied at our quad level, as you know, the quad level IR is whenever the branch is generated, conditional and unconditional, it is always associated with a label, and so we will use that as a fact of starting the basic block or identifying the leader here. Now, the second statement, the second thing which may not be exactly clear is, suppose we have a branch that is terminating a basic block, because now you can see that the next statement after that branch is not going to execute exactly in the same order unless it's a fall through case of a conditional branch. If it's an unconditional branch, there's no way that second statement will execute anyway in that order. So that guarantee is broken there, and therefore the statement following any branch, conditional, unconditional, is a leader because that guarantee is not there. Okay, it's very easy to see in both the cases. And the other one is, of course, a return statement, which is similar to a branch, except that the control flow is branching out completely out of the current unit of execution and going back to the point of call. So that behaves like an unconditional branch to the point of call or the call site, which is a special case of a branch. And so anything that follows these two cases is also a leader because it does not follow the guarantee of a basic block, and therefore it starts a new basic block of execution. It does not extend the current basic block. So these are the three conditions. You can see that they cover all these kinds of cases. First is very simple. Second is about target of a branch, which stops upward execution extension. The third one is downward extension is stopped of a basic block, and therefore it starts a new basic block using something which comes after the branch or return statement. So let's apply this to these simple code. It's a pseudocode coming out of some simple syntax here, which is doing some dot product for two vectors, and it is basically the IR looks like this, which is shown on the right hand side. And this IR is given to us by some front end, which we don't know anything about. And our goal is to therefore detect these basic blocks in the maximal way by applying this algorithm. So let us apply this algorithm here. And this is a function call, by the way, or a procedure call, which is doing that, and so on. And the first statement is the leader, where the things really start executing as far as the intra-procedural execution starts. You can see that if we keep going down at the branch number label 3, we have a branch. So therefore, a new basic block starts there. You can see between 2 and 3, the basic block is broken because of this branch, because they don't execute in one after the other in a linear way. And so that's why this new basic block, which is starting with the target of the branch. And, we have a nice big basic block. If we keep going down, there's no target, there's no control flow statement which breaks the control flow, etc., etc. But at the statement number 12, we know that we have a conditional branch, and anything that comes after this particular branch, even if it were unconditional or if it were a return statement, etc., this guarantee of the two executing in that order always is broken, and therefore the statement following this branch, number 13, which is rule number 3, starts a new basic block. Okay, so if we do this, then how do we know we form now the basic blocks from these leaders? Well, there we use a simple definition of linear control flow in the basic block. From one leader to the other, except the next leader, all the statements are a part of a current basic block, and that's what we keep doing. And we start at 1, we end at 2 because number 3 is the leader itself. So that's the first 2 are one basic block. Next group of statements is all the way down to 12 is a basic block. You can see that that basic block is terminated by a conditional branch. And 13 starts yet another basic block, third one, and so on. So you can see here that this representation has yielded some very interesting things to us of linear control flows and that maximality and so on. And if we try analyzing it from top to bottom and pick up some properties of those, we will be able to do certain optimizations there. I'd like to draw your attention to one of the properties that we'll be able to use for this simple example in B2. Of course, we don't know what B3 is since it's a simple example. B1 is too simple. But in B2, you observe that in statement 3, we have done 4 times I as a sub-expression there, generated its value in T1. And then between those 2 points, you can see that I has not really changed between 3 and 5. And the same sub-expression is again evaluated in 5. And its property is, its value is assigned to T3. So you can easily see here in this case that no matter how we enter this block B2, we'll first always evaluate statement 3 and then following that statement 5. And the value that is generated in statement 3, 4 times I, will be exactly always same as I in statement 5. We might bring values of I. That's a different story. But no matter what we bring in, let's say we bring in I is equal to 5 in one case, to T1 being 20, T3 also being 20. Next time we bring in I is equal to 100, let's say. So it's a different value of I. But again, T1 and T3 will always be the same. That's because of this particular property that I has not changed. And we always evaluate 4 times I before doing the 4 times I again in 5. And therefore, the second evaluation of 4 times I is redundant and can be gotten rid of. Purely looking at the basic block itself, without worrying about anything about I values, where they are coming and what they are and so on. So this allows us to do certain optimizations which are intra-basic block, within the basic block, or local optimizations just by building this representation. And since this is a maximal representation, it gives us the maximal opportunity to do so. Again, if we had just limited ourselves to number 3 being a basic block itself, we lose this property. We lose this maximality. And therefore, the scope of optimizations will become very almost insignificant or useless. So, of course, does it give us all the opportunities? I would not say so. And that is the reason for building the flow graph based on this. So far, you can see that we only have blocks. We have no idea of how the control goes from one block to the next block or whatever. We don't know what will happen after text statement 12. And we don't know what will happen between B1 and B2. All these kinds of things are unknown to us. And if we know those, and if we build that representation, that will be the next step, which is called as control flow graph. And that will allow us to do even more interesting changes to the program, even better ones. But even in the absence of that, we can do this change, which I wanted to point out between statement 3 and 5. Any questions? Okay, good.
I think we're okay. We're discussing some of the basic block rules in the chat about how about how new basic blocks are started. But I think we've addressed all of the questions. I think we're good.
Thank you. Yeah, and this is recorded, so you can always go back and post some follow-up questions if you have. And now, so let us see if we can find some better properties across basic blocks, which will tell us that, hey, from this basic block to that basic block, here is how we can go. And finding that is a part of our next endeavor, which is called as the control flow graph. So what is the representation? The representation is each one of these nodes are basic blocks, and these are maximal groups of IR statements, and they always execute linearly. That is, when we enter them, we always go from top to bottom, one statement at a time, and that's the order of execution of the control flow within the basic block. So we follow that order. So if we look at a basic block and look at the lexical order of execution from top to all the way the bottom, it gives us a sense of what is going on, which value is getting generated before what, and which is getting used to where, and how it is getting propagated within the basic block. Agreed? So now the next one is, how do we find out how the values go across the basic blocks? And for that matter, we must find out again the flow of the control across basic block. And for that, we need data, and that is what is control flow graph. So what happens is, again, consider it from a standpoint of a function or a procedure. We first hit the first basic block, and that is where we start execution. It is called as a start node. So in this case, you can see that the start node is B1. We'll come in here and we'll start executing these initialization statements. And that's where the execution will start. So that's a root node or a start node of execution. Now, after that, things will start happening. And main thing that will happen is because of these branches that we have, those branches, if they are unconditional branches, like go-to kind of statement, we will know that the control flow will exactly go along that particular path. But if they're conditional ones, like this over here, we know that there will be two paths here, two outcomes. One is when this condition is true, we'll go to 3. If this condition is false, what will happen? We'll fall through here to number 13. So we'll put this edge here between 12 and 13 when the is false. Otherwise, when it is true, we'll put an edge like that. So those are simple cases. Now let me ask a third question. What will happen between B1 and B2? You can easily see here that the control always comes from B1 to B2. Look at this particular one before we did this. Okay, so we were here and we were just executing things coming down. So from some basic block in which there is no branch here, the control always falls through to the basic block, as simple as that. When there is a branch here, if it's a conditional one, it will fall through or it will go along this edge. If it is an unconditional one, there will not be fall through, but it will go along that edge. So all these to be captured here using some simple rules, and those are the ones which lead to this simple algorithm that when we don't have a branch, there's always fall through. Let's number 2 to 3. When we have a branch, if it's a conditional one, then there will be a fall through as well as the target edge. And if it's an unconditional one, then there will be only the branch. That's it. And if we apply this particular rule or set of rules, here is what we'll get. There's a branch from last statement of B1 to the first statement of B2. Then we follow the branch, we put that. So that's one rule. The other two cases that I mentioned are all about fall through. So the control can fall through between B1 to B2 because B2 immediately follows B1. And it does not end with an unconditional branch. That means it has a simple statement like the one which we saw between B1 and B2 in the previous example. It will simply fall through. And of course, the case of fall through in this particular case is when it does not have any kind of unconditional branch. Or it just falls through, as in particular case over here. So using these two rules, we are able to get this simple basic blocks. So you can see that it does not end with an unconditional branch, and we have a case of fall through here. In this particular case, rule 2. Because 2 is not an unconditional branch and B2 follows B1 lexically. So it's a simple fall through case. The next rule you can apply is because of the target of the branch. So we follow the branch and we go through in this particular case using rule number 1. And the third rule, the third case is here, which is again the fact that it is not an unconditional branch. Okay, so because if this were just goto, for example, then there will not be a fall through here. So since it is not the case, it will be either a conditional branch which will have a fall through, or it will be a simple case like this, which is not a branch itself, and both are combined by this particular rule. It may be a little clumsy to remember it this way. Keep it simple, in my opinion. If it's not even a branch, there is a fall through. Remember that. The second one is if it's a conditional branch, there's definitely a fall through in that. And then the condition becomes false, it goes fall through. Then the case of a branch itself, you have to go through the edge where the label is to go along the branch. That's the control flow. And obviously, if it's a unconditional branch, then there is no fall through because obviously it's unconditionally true, and you will always just go along there. So if this predicate were absent, for example, there was just goto, then there will be only this particular edge, no fall through here. Okay, so remember it this way, and that leads us to this nice representation. You can see pretty much the original loop that we have is captured here in this nice representation. We have an initialization part of this loop. Then we have this body of the loop. We have an iterator here, which is checking the condition on I, and then it is exiting the loop. So this whole structure, which was present in our source code, is captured here at the IR level. And this is important because this is captured now in a maximal sense of the basic blocks and the control flow within. Now, what can we do by noting this particular structure, which is outside of what we saw in terms of basic block? We can do a lot of different things, and this is the most important structure that is used for our data flow analysis across basic blocks. You can see here that first of all, we can answer questions across basic blocks. So somebody might say, hey, replace this I with I equal to 1. Is that correct or not? You can see that that question is no. because although I is equal to 1 is one of the values which comes in from B1 to B2, that's not the only value in statement 3. The other value of I which comes in because of the control flow edge, which is returning control from 12 to 3, and that brings a new value of I here, and that value is not equal to 1. So we cannot do this optimization. Okay, so in some cases of flow programs, maybe that value is same as what comes from the top, and we can do constant propagation and things like that inside the B2, but not in this case. And then there are many other properties which allow us to do the analysis of redundancy and other things across basic blocks, which we cannot do otherwise. You can easily construct some examples thereof. And so this is the representation which will get us to a very precise view of the world in terms of how the data flows along these control flow edges. And we'll be using that for doing certain analysis. Now you can see that after having discovered the structure, one of the key questions that the compiler has to answer is, where do I focus my analysis? Where do I focus my optimizations and so on? Why is that important? That is important because remember the rule, 80-20 rule, 80% of the execution time is spent in 20% of the code. And what is that 20% of the code? That is nothing but the loop. So you can see that the heavy execution will occur here in B2, and that is where we should be really focusing, and that is uncovered by this particular control structure. Now what we need to understand is the control flow graph is a graph, but it doesn't show us what is a loop. So the next step, if we really want to focus the optimization efforts, is to be able to discover the loop. And from the graph that we have, how do we discover the loops? What are the loops? How do they get discovered, etc.? That will be the next step in terms of the control flow analysis. All that is a part of control flow. It's not data flow at all yet. So from the graph to generate the loops or discover the loops will be the next step in terms of analysis. And we'll continue this discussion in the next lecture. So this point will stop, and thank you, and we'll see you in the office hours, those of you who want to talk.